They find it very strange because when they were here, they measured the speed of light as being 300,000 kilometers per second. Spaceship was 300,000 kilometers long, and they verified it by, sending a burst of light from one end to the other because they know the speed of light is 300,000 kilometers per second. But when they do the same thing here, they get the same results, even though their spaceship is shrunk to half length. But they don't know that, because even if they measured it with a wooden ruler, well, if you take the wooden ruler and it's oriented in the same direction as the spaceship is going, the wooden ruler shrinks as well, but they don't know that. So if they measured the spaceship with the wooden ruler, they'd still measure it as being 300,000 kilometers long. So due to their measurement instruments changing, even though they're going in a specific direction at a high velocity, no matter which way the light is sent, they still measure it as being the speed of light. So it seems like to them, the laws of physics here are exactly the same as the laws of physics there. Are we at rest now and we're moving before, or is it the other way around? They can't tell. It makes it seem like everything is just relative because nothing seems to change. Meanwhile, though, from an external observer's point of view, who in this case is at rest in space, he sees things differently. And so this is how the external observer sees it. This is how those on board see it, and so forth. But understanding what's going on here, understanding how the measurement instruments change, we can create transformation equations to go from one to the other or vice versa. So for instance, here we have the equation to calculate this offset here, the time offset. And they wouldn't necessarily have to send the light from one end to the other, which is related to the length. So they could send it halfway, a quarter, whatever. In other words, a certain distance across there, a certain x distance. And so since they still think that this is 300,000 kilometers long, this x distance they would think as being 150,000 kilometers, for instance, right? That's what their rulers would tell them. And so that's what we would call, we could change this length, therefore, to x prime. In other words, x distance as they see it, because as far as they're concerned, nothing has changed. So here we have our equation which produces the 0.866. Then you add to that the t prime. That gives you 1.866 because they measure a time period of 1 second, right? That's time as they see it. And then that's the offset. Then if you divide that by this equation here, the square root of 1 minus v squared over c squared, that gives you the result of t as it's seen by an external observer. So this would be 3.73. Take this 1.866, 1 second, plus the 0.866 divided by this, which remember turns out to be 0.5. So 1.866 divided by 0.5 equals 3.73. So that would be a conversion equation to transform from their point of view to an external observer's point of view. To go the other way around, you just change this to the x as seen by the external observer. This becomes time as seen by the external observer. This becomes t prime, time as seen here, and you convert this to a minus. So this would be the 3.73 minus whatever this turns out to be divided by 0.5, which will result in 1 second as they see it. So it's, again, converting from one point of view to the other. Now, not all of these conversions are limited simply to time. It's also measuring distances. We can convert, by understanding how the measurement instruments change, we can transform from one person's view of a certain distance to the other and so forth. And so what we'd end up with is the equation x minus vt over the square root of 1 minus v squared over c squared, and that would equal x prime. What is x? Well, x is a distance in the x dimension from the external observer's point of view, who's at rest in this case. So that is the distance the light traveled from his point of view. Now the light traveled from one end of the spaceship to the other, but also the spaceship was moving. So the light traveled the distance the spaceship traveled and the length of the spaceship itself, because it started at the rear, ended at the front. So x is a combination of the distance the spaceship moved plus the length of the spaceship. What is VT? Your velocity of the spaceship and the time that it moved, which tells you the total distance that the spaceship moved. So if you take x, the complete distance, minus the distance the spaceship moved, you're left with the length of the spaceship itself, which, if you recall, to an external observer, appears to be 150,000 kilometers because it shrunk to half length. Divide that by this, which turns out to be 0.5, and that gives you 300,000 kilometers. Because that's exactly how they see it. They are completely unaware that their spaceship is shrunk. So their x measurement, if it's the length of the spaceship, for instance, is still 300,000 from their point of view. So there's another transformation equation. Now, when you're moving across time like this and you start moving across space, rotation occurs, thus you begin to lose out on depth of space. The spatial length contracts, right? But that's because you're rotating across a specific axis, right? You're losing out on a specific axis, this case being the x-axis. Therefore, the y-axis and the z-axis are not affected. Therefore, y prime equals y and z prime equals z. So there we have transformation equations basically taken care of. Now the next thing you'd want to do is, well, that was relating light to constant motion, right? That produces this magic thing of where the laws of physics seem to be exactly the same here as they were over there, and so they measure the speed of light over here as being exactly the same, even though it's not necessarily the case. So the next thing you want to do is deal with objects moving slower than the speed of light. So what we'll do is introduce some magic guns and bullets. We put a gun and a bullet at this end, and a gun and a bullet at this end, and these guns are able to fire these bullets at 260,000 kilometers per second. So these are fast bullets. So if you fire the bullet, if Mr. A releases or fires the gun at his favorite time, 12 o'clock noon, that bullet would reach Mr. B, preferably without killing him, at roughly 1.154 seconds after 12 o'clock noon. It takes longer than a second because it's moving a little bit slower than the speed of light. Anyways, it reaches him and he looks at the clock and says that's exactly the time it should have arrived because the bullet is supposed to be traveling at 260,000 kilometers per second. Perfect. Then he tests out his prototype gun, shoots a bullet over to Mr. A at 12 o'clock midnight, and sure enough, it reaches Mr. A at 12 o'clock midnight plus 1.154 seconds. Excellent. Then they fire their rocket engines and they're moving across space at the velocity of 260,000 kilometers per second. So now you have the spaceship moving at 260 along with the gun. Then you're going to fire the bullet again at 12 o'clock noon, and the bullet will be going at 260 relative to the gun and the spaceship. Therefore, you'd think that the total speed of the bullet would be 260 plus 260. In other words, 520,000 kilometers per second. But that's obviously impossible because the bullet, for instance, was going in this direction to begin with. But even if you pushed it across here, so it's moving across space only, the maximum speed you can go is 300,000 kilometers per second because that's what this constant motion produces. But then you think, but wait a second. Everything seems to be the same here, so the laws of physics are the same. Therefore, they would still measure a time of 1.154 seconds after 12 o'clock noon at this clock, Mr. B. So when the bullet reaches him, he would measure a time of 1.154 seconds after 12 o'clock noon. So that would be his T prime. Now, if we were taking this equation here, but reversing it, such as this is positive, this is T prime, and so forth, we add the offset, clock offset, which is 0.866, which gives us a time of 2.02 seconds. And then we divide it by this, right, which ends up being dividing it by 0.5, which equals 4.04 seconds. Therefore, to the external observer, it appears as though it takes the bullet 4.04 seconds to cross that 150,000 kilometer distance. So if you take the 150,000 kilometers divided by 4.04 seconds, you find that the speed of the bullet relative to the spaceship turns out to be 37,000 kilometers per second. And then there's the speed of the spaceship itself is 260,000 kilometers per second. So the total speed is 297,000 kilometers per second, approximately, because these are rounded off numbers.